session. In this time, we are going to listen to Pedro Luis del Angel from CIMAT. His talk is Cohomological Chow groups. Please.
After Hanamura, thank you. Well, first, thank you to the organizer for the kind invitation to be here. It's always a pleasure to be in Oaxaca. And thanks to all of you for being here. So I'm going to talk about a work of Hanamura. It's not something, most of the talk is about the work of Hanamura. Only at the end, I will say something that we are interested on. So let me begin with the classical Chow groups defined by Spencer Bloch. So Spencer defined the simplicial objects like this, just a fine line but, in a twisted position. Define a space, of dimension q on aq plus 1. And then, of course, you have really a simplicial object. You can embed the single point in the line in 2 vertices and the line in 3 different boundaries of the triangle and so on. So if you have a quasi-projective variety, let's say over C to simplify things, you can take the group generated by codimension K varieties inside of X cross delta Q. This is a huge group. But then you take the elements of this group which intersect properly all the faces, meaning the dimension and the codimension with the intersection of the faces is less than or equal K. Bigger than or equal K. Taking the boundary of those elements makes a complex out of this, and then you take the cohomology of the complex. So you have a complex, and the Chow groups defined by Bloch is just the cohomology of the complex. So these groups are very nice. They have some nice properties. For instance, for Q equals 0, you just recover the classical Chow groups. If X is smooth and irreducible, then you have a multiplication map. So this is a cohomological theory, generalized cohomological theory. And it also has a localization sequence if X is smooth. So it's really like a cohomology. Another property is that the Chow 1 group for n is always 0 if n is different from 0 or 1. And Chow 1 x1 is always C star if X is a smooth variety. And the most important thing on the time that they were introduced is that they are degraded pieces of the K theory, of the algebraic K theory. So this is an algebraic way to compute algebraic K theory up to torsion. Now, if X is not smooth, then you don't have localization sequence and you don't have multiplication. So what can you do if X is not smooth? So in order to do something, in order to be able to do something, we need to talk about hyper-resolutions. One way could be speak about hyper-resolutions a la Deligne, but this is very complicated, especially because it is usually infinite. The hyper-resolutions a la Deligne are infinitely long. So it's hopeless to compute anything. Unfortunately, there is work done by Navarro, Aznar, and Guillén, and some other Spanish people. But around the same time, James Carlson had a different approach to the same situation. Navarro, Aznar, and Guillén call it cubical hyperresolution. Carlson's called them polyhedral resolutions. So I'm going to explain the Carlson's approach because it is easier to follow. The other one is quite too technical, but they are equivalent. So take any polyhedron and think of it as a category. So the object of the category are the faces of the polyhedron, and the arrows are just, there is an arrow if A is a face of B. I mean, yeah, it's an inclusion. Okay? And then a P scheme is a functor from the opposite category of the polyhedral to the category of schemes. So if every time you have a face, you have a scheme, and if you have an inclusion, then you have a reverse morphism. Okay? That's a, that's a P scheme. If the polyhedron is just one point, then a Q scheme is just a scheme with identity morphism, nothing more. And let me say, give some kind of examples. If you have Q plus 1 linearly independent vectors in Rn and Rq, Q plus 1, sorry, in Rq plus 1, then you can define this, which is just another way to define the polyhedron, pyramid or whatever. You take the sum of the convex sum of these vectors with coefficients adding to 1, and they run between 0 and 1. For instance, for B0, B1, which is the line, the segment 0, 1, this will be a polyhedral object. You associate something to the line, and then you have, so say it like this, then you have two vertices and one side, and then you have a scheme associated to the side, to the length, and two schemes associated to the vertex. Since every vertex is inside the segment, then you have a morphism from here to there and from here to there. That's a B0, B1 scheme. I would like to call them delta 1, but since I use delta 1 for something else, then I choose this notation, which is not so nice. Anyway, so this will be like a delta 2, and then you have a triangle. So you should have a scheme corresponding to the triangle itself. Then you have three different schemes, in principle, three different schemes for every side, and then three different schemes for every vertex. And then you have three morphisms from the scheme corresponding to the triangle to the different side, to the schemes corresponding to the different sides, and so on. So you should be getting an idea what a polyhedral scheme is with these examples. And then the morphism of polyhedral schemes is given by the following data. First of all, you need a functor between the polyhedral, considered as categories. And then you need morphisms of schemes for every face on the polyhedral scheme associated to P into the corresponding face of the polyhedral scheme associated to Q. In such a way that you have commutative diagrams. Okay? Okay. In particular, if you take the polyhedral corresponding to one point, and P is any other polyhedron, there is a unique functor from P to Q, sending every face to the point, and then a morphism of polyhedral schemes between the polyhedral schemes associated to P and the polyhedral scheme associated to the point is just a collection of maps from every face into Y with commutative diagrams. Okay? So given a polyhedral scheme, we define its geometric realization as the union of all the faces modeled out by some equivalent relation, which is the obvious one. You compare every point with this image on the faces, and you make them coincide. Now I can come to the definition, to the real definition. If you have a polyhedral map, you say that this is a polyhedral resolution of Y if the geometric realization of this polyhedral scheme is homeomorphic to Y. In the original paper of Carson, he was not taking this to be, sorry, he was just considering homotopy type because he was mainly interested in cohomology. And this was already coming back to Siegel. This is an idea of Siegel to compute cohomological K-theory and algebraic K-theory as cohomology theories. So this is a very old idea. But for the definition that we want to do, we really need this to be homeomorphic. So let me make an example. Suppose C is a singular curve. You take its normalization, the singular locus, and the exceptional divisor. Then this square is a resolution, is a B0, B1 resolution of C. Right? Because if you forget the C, this is a B0, B1 scheme. And the maps are commutative. And of course, the geometric realization of this B0, B1 scheme is nothing but C. You are identifying the fibers of the exceptional divisors with the points they are coming from inside the normalization. So this is just doing the blowdown. You are contracting the points, so you are recovering C. If Y is just a strict normal crossing divisor, I just put 4 because it is easier to make the picture, but it doesn't matter. You may take a different zone. A strict normal crossing divisor, meaning that all the intersections are smooth, either smooth or empty. Then you have resolution, a simplicial resolution of Y, where X0, or I call it B0, B1, so it's a simplicial resolution, where X3 is just the intersection of all the divisors. X2 is the intersection of 3 of them, all the intersection of 3 possible of them. X1 is all possible 2 intersections, and X0 is just every single divisor. And again, if you consider the geometric realization of this is, you recover Y, because you're taking the disjoint union of the divisors and then identifying the intersections. So you recover Y. So if all the schemes of the skeleton, let me call this the skeleton of XP, are smooth, we say that the polyhedral resolution is smooth. And by iterating this construction associated to the line, where you have something, so you could take any scheme, any variety, the resolution, take blobs, take any resolution, take the singular locus and the special divisor associated to that. This may be or maybe not smooth, but you could continue doing this process to E, or maybe to sigma if it is not smooth. You can iterate this process, and iterating this process, you can always get a V0, V1 to the M resolution, which if you make a contraction, because in the process may appear some phases that are repeated, some schemes associated to the phases may be repeated. And of course, the morphism is the identity. So if you are identifying X with itself, you can erase one of the pieces. So if you take this, iterating the construction, you get a resolution with this cubical resolution. And then you can eliminate some redundancies. Then you produce a finite simplicial smooth resolution. And we call that a hyperresolution. It is finite because of the process itself, because you are getting divisors above something which is smaller dimension. And then you desingularize this, and every step you are getting something of smaller dimension. So the process is finite, and you get a finite hyperresolution. which is exactly the opposite to what usually happens for the linear hyperresolution. It is normally infinite. Now, if you have a quasi-projective, if X is quasi-projective and X dot is a hyperresolution, we define the total complex for X. I mean, we define this complex for X as the total complex associated to the hyperresolution. And this will be a complex, and then the cohomology of that complex is the cohomological Haiger-Chow groups of Hanamura. Then, of course, this has some properties, very nice. If X is, well, the first one, which is the most important one, is it does not depend on the chosen hyperresolution. You can change the hyperresolution as you like it, the one that is better for your taste or to more manageable or whatever. If X is smooth, since it doesn't depend on the hyperresolution, then this coincides with the classical Haiger-Chow groups of block. And for these groups, you have a localization sequence, regardless whether X is smooth or not. You have always a localization sequence. So this in particular is very important. We use that property, for instance, to produce a going up theorem in K theory. So imagine you have a family, say, of elliptic curves over the puncture disk. And then above zero, you have a singular fiber. Right? And let me write it like this, but this, and take a cycle in Chow 2 xt1, which will be something living in, I mean, it's a class of something. If you take an element here, it is the class of something living in xt cross delta 1 of codimension 2. Well, I will not represent it really in xt cross delta 1. I just draw a picture like this and assume that the picture is like essentially as I draw it, meaning that you can extend it to the exceptional fiber. You can extend the cycle to the exceptional fiber. Then, because of the localization sequence, you have a map from, well, you could do this even if it is not a disk, but if this is the spectrum of a ring, of a discrete valuation ring. Then the generic fiber is one fiber. You can extend it, so you have a map from xt1 to Chow to X, which is the whole family, and then to Chow. Well, I should be writing it all the time, sorry. I should write CHC2 xt1 to CHC2 x1 to CHC2, and then the special fiber 1. Now, if the generic fiber is smooth, this is nothing but CH2 xt1, which is a piece of the K1 group of xt. This will be, if the model is smooth, this will be Chow 2 x1. But then the fiber is singular, the special fiber is singular. So this has a component coming from the singular point, but the singular point is smooth itself. So you have something coming from Chow 2 point 2, which is a piece of this. And so you are getting something in K2, starting with something in K1. So this process can be repeated several times, and then you can come from a class in some K-theory of some variety. By doing some deformation, you can get a class in a higher K group of a different object until you end in a point. So that's one of the main, I mean, this localization sequence is really important. We were able to produce something out of this. And another thing is that if T is a curve, possibly singular, then these cohomological higher Chow groups are 0 for n bigger than 1. And they coincide with C star if n is 1. Okay, that's more or less what we know. If S is a singular surface with isolated singularities, and the exceptional divisors above the singular points are trees, then again, the cohomological Chow group 1 Sn is 0 for n bigger than 1, and cohomological group 1 is C star. So a reasonable question, which I asked to one of my students, is prove the same, say for a three-fold with a singular, with an isolated singularity. So it's something that he's trying to compute right now. It seems to be very likely the case. It's not too difficult. It's just an exercise for him to do some calculations on this. And then for smooth varieties, we know by the work of Webowski that the Bloch higher Chow groups are related to the motivic homology. So a more interesting question, and of course much more difficult question, is what is the corresponding analog for these Hanamura cohomological higher Chow groups? So this is, of course, a question that I will hope my student is able to solve, but it's not so likely. We will see, and we are working on trying to do something with this question. And that's it. Thank you very much.
Do you have questions for the speaker?
Do you have a candidate for the
For the motivic, no. No. I mean, I have a candidate, the obvious one, because the point is if it is not smooth, Bloch's group is not isomorphic to the motivic homology. So my guess is that these cohomological higher Chow groups will be related to the motivic homology, but I don't know how to prove that now.
I remember there was a problem with Bloch definition originally because you had to have some probabilistic assumptions, some kind of formula. I seem to remember that Bloch original definition, there was some...
That's right, but it was solved by Mark Levin. So you could also change, I didn't want to change the notation, but you could replace the deltas by P1 minus 1 to some power, and yeah, that works, yes.
Any other question? If not, let's thank the speaker again.
And we have
a break of 5 minutes.
5 minutes, ¿sí me tomé la media hora? Por fin.